Hi everyone. Today we're going to talk about eigenvalues and eigenvectors, which are really cool special vectors in linear algebra. So let's begin by stating the definition of what these things are. An eigenvector of an n by n matrix A is a non-zero vector, let's call it x, such that a times x is equal to lambda x for some scalar constant lambda. Yeah? So this is the fundamental definition here. Ax equals lambda x. What we really need to pay attention to is that an eigenvector must be non-zero. An eigenvector must be non-zero. Lambda is allowed to be 0, but the eigenvector itself cannot be 0. And we can only have square matrices here. The scalar lambda is called the eigenvalue associated with the eigenvector x, or corresponding. Yeah? So these two are associated. An eigenvector has an eigenvalue lambda. Yeah? So an eigenvector x has an eigenvalue lambda, satisfying ax equals lambda x. So let's see some numerical examples. Let A be the fun matrix 1, 6, 5, 2. Let's start off by asking an easy question. Is the vector 6, negative 5 an eigenvector? And I'm going to be lazy here, guys. I'm just going to call it an e-vector, but it means eigenvector, okay? Eigenvector. So here, try to pause the video, see if you can figure out what to do here. So let's just compute matrix vector multiplication, right? I know I need to look at the matrix times an eigenvector. Better be some scalar constant times that eigenvector, right? So let's do the multiplication. So let's call this vector x, and let's compute a times x, which is 1, 6, 5, 2, times the vector 6, negative 5. This is equal to the vector 6 minus 30, which is negative 24, 30 minus 10, which is 20. Well, how do we know if this is an eigenvector, right? I need to say that this is or is not some scalar constant times 6, negative 5. Well, how many times does 6 go into negative 24? Negative 4 times, right? And indeed, how many times does negative 5 go into 20? Negative 4 times. So this is negative 4 times the vector 6, negative 5. So is it an eigenvector? Yes, it is an eigenvector. And moreover, what have we found? We have found its corresponding eigenvalue, negative 4. So before we move on and do more examples, let's talk about what this is doing. Eigenvector, eigenvalue, eigen comes from German, and it means something like, the same. Yeah? So what is A doing to this eigenvector 6, negative 5? What's the result of applying the matrix A to the vector 6, negative 5? Well, it kind of preserves the vector 6, negative 5, doesn't it? Except all that it does is scale it. Yeah, it scales it in this case by some fixed constant negative 4, but the vector itself has not changed directions, right? Other than flipping, of course. Yeah, but the angle has been preserved here. So eigenvectors mean that whenever you apply the matrix A, it stays the same. The direction is kind of preserved here up to some scalar constant. Yeah? Hopefully that makes some sense. Let's do another example. So suppose we have our favorite matrix named A equals 1, 6, 5, 2. We'll be really creative here. Let's ask another question. Is the vector 3, negative 2 an eigenvector? And remember, E vector, I'm being lazy, that just means eigenvector. Pause the video, see if you can do this yourself. Well, let's compute the multiplication. We want to compute 1652 times our vector 3, -2, which is going to be, let's see, 3 minus 12 is -9, 15 minus 4 is 11. And is -9, 11, a scalar constant times the vector 3, -2? No, this is not some scalar constant times 3, -2. Yeah? Because if it was, lambda times 3 is -9 means that lambda would have to be -3, right? But if lambda is -3, this entry would have to be 6, but it's not. So therefore, there's no scalar constant such that lambda times our potential eigenvector gives you the result of applying the matrix. So this is not an eigenvector. This is not an eigenvector. Eigenvectors are special. Yeah, eigenvectors are very special for us. So how do we find them? How do we find them? Yeah? And these have some really nice applications that we'll see later, but for now they're just kind of going to be nice vectors that are that don't have their directions changed whenever you apply the matrix A. Yeah, they're kind of fixed under the transformation T of x equals AX. So how do we find them? So we want to find vectors and values that satisfy the equation AX equals lambda x, right? This is what we want. How do we get it? Well, this means that AX minus lambda x equals 0. Yeah? We know from algebra that if we ever want to solve for x, get everything on one side and then solve in some way, right? In factor. Factor and solve. How can we do this? Well, A is a matrix. I need a matrix in this term to make things kind of gel together. So let's rewrite this as AX minus lambda times the identity times x. Yeah? And just as a note, guys, this 0 over here is the vector 0. This is the vector 0. And so now what can we do? I can factor out from on the right-hand side the vector x. So I know that x must satisfy a minus lambda I times x equals to 0. Yeah? So x is a vector that satisfies this thing times x equals 0. Where have we seen that before? That's a null space, isn't it? Yeah? An eigenvector is a vector x yeah? We have an eigenvector if and only if x is in the null space of this funny matrix A minus lambda times the identity. Yeah? And if A is an n by n matrix, then I is the n by n identity matrix. Yeah? And this is true for some lambda. For some lambda. So we have an eigenvector, right? We have an eigenvector. If A minus lambda I times x is 0, which means that we have an eigenvector if and only if it's in the null space of that matrix A minus lambda I for some fixed scalar lambda. So when do we have an eigenvalue? If and only if. What do we know about the null space now of A minus lambda I? When do we have an eigenvalue? What must be true about the null space of this funny matrix A minus lambda I? Well, I know it has to have something in it. And what do we know about x? X is not 0. So if x lives in the null space, then the null space has to be something more than just the 0 vector. Yeah, and that's just the 0 vector here. Sorry, it's off the screen there. So we know we have an eigenvalue if and only if this null space has something beside the 0 vector. Well, this is a square matrix, and it has more in it than just the 0 vector. What does that mean about its invertibility? It means it's not invertible, right? It means it's not invertible. And so let's apply some of our knowledge from the invertible matrix theorem. What do we know if it's not invertible about the determinant of A minus lambda I? The determinant has to be 0. Yeah? And this is really, 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 really important with a smiley face. Yeah? This will be something called a characteristic equation for us. So if we want to find an eigenvalue, all that we need to do is compute A minus lambda I, take a determinant, and set it equal to 0, and solve for lambda. How do we find a vector x? Given that lambda that we found, we need to compute the null space of A minus lambda I, yeah? And x will be some element there. And if you want a basis for the null space, we can find every eigenvector. Yeah, and we'll see this going forward. So, we have this really interesting null space. The null space of A minus lambda I has a really fun name. It's called the Eigen Space. Corresponding to lambda. Yeah? Note. What if lambda is 0? What if lambda is 0? What do we know about the determinant of A? Well, if lambda is 0, the determinant of A is going to be equal to the determinant of A minus lambda I. Yeah? If lambda is 0, then we have that the determinant of A is just the determinant of A minus lambda I, right? Well, that's kind of interesting. Let's see. What does that mean? If A is invertible, what must be true? If it's invertible, what do we know about the determinant of A? It's not 0, right? It's not 0. So if the determinant of A is not 0, then we know that the determinant of A minus lambda I is not 0. What therefore do we know about lambda equals 0? It cannot be an eigenvalue. So if A is invertible, then lambda equals 0 is not an eigenvalue of A. If A is invertible, then lambda equals 0 is not an eigenvalue. Okay? And this will be helpful for us. All right. Okay. Suppose we have a matrix A, and suppose we have some eigenvector x with associated eigenvalue lambda. Yeah? We have an eigenvector x, and of course, what do we know about x? X is not 0. Lambda could be 0, who knows? Question. Is 7 times x an eigenvector for A? Is 7 times x an eigenvector for A? Pause the video, see if you can figure this out. Well, let's do this in two different ways, right? Before we even do any computation, where does x live? X lives in the subspace of some funny matrix, right? Or no, the null space, sorry. X lives in the null space of some funny matrix. The null space is a subspace. And what do we know about subspaces? They are closed under scalar multiplication. So we know before we do any work that this will be an eigenvector, because we know that it's associated with the null space of some matrix. How do we compute this, though? Well, if it's an eigenvector, let's just try to compute A times 7x. And see if we can write this as lambda times 7x, right? Well, what can we do? We can pull out that scalar constant 7. And what's ax equal to? That's equal to 7 times lambda x. And let's use associativity and commutativity of scalars, and we have that this is now lambda times 7x. And so indeed we do have, yes, 7 times x is an eigenvector. So what's important here is that lambda has not changed. The eigenvalue is fixed in this equation, right? But with a fixed eigenvalue, we have total non-uniqueness of eigenvectors. Okay, they're not unique. They live in a subspace, right? So there are tons and tons of these things from which we can choose. Yeah? Eigenvalues are unique for a matrix. The corresponding eigenvectors are not unique. So let's do an example to actually compute eigenvalues and eigenvectors for a matrix. Let A be your favorite matrix, 3, 2, 3, 8. And our goal in this exercise is to find the eigenvalues and the eigenvectors. Okay? Remember, what do we need? To find the eigenvalues, we need to compute that characteristic polynomial, determinant of a minus lambda I. Yeah? We know the eigenvalues lambda have to satisfy this equation. So we're going to compute that in a second. And once we find our lambdas, with our lambdas, to find the eigenvectors, well, we just said that they're not unique. So what do we mean by finding the eigenvectors? What we're really going to do is find a basis for the eigenspace. Yeah? And to do that, what do we need to compute? So we want to find a basis for the null space of a minus lambda I for each one of those eigenvalues lambda. So let's get to work. Let's compute. What is the determinant of a minus lambda I? Right? And this will be equal to 0. Well, it's the determinant of, and I'll write it out just for fun. I'll probably never do this again, but we'll write out exactly what it is. Here's A. What's lambda times the identity? It's lambda 0, 0, lambda. Right? So we want to compute the determinant of the matrix 3 minus lambda, 2, 3, 8 minus lambda. Oops, and that's off the screen. Yeah. How do we do this? This is going to be this entry times this entry, 3 minus lambda times 8 minus lambda, minus 6. Sorry about that. And what are we solving for? We're solving for lambda. And remember, this is called a characteristic polynomial. And let's expand this. How do we solve this? So we want to solve 0 equals to 24 minus 11 lambda plus lambda squared minus 6. And if you do a little bit of algebra, you should see, I hope, that this factors as lambda minus 9 times lambda minus 2. And all of that's equal to 0. So what are my two eigenvalues? We have lambda equals 9 and lambda equals 2, or our eigenvalues in this matrix. So we found our eigenvalues. And remember, the eigenvalues are going to be unique for us. Given a matrix, you have unique eigenvalues. How can we now find a basis for the eigenspace? Let's see. Well, let's kind of make a list. If lambda is 2, then we really want to compute the null space, right? A basis for the null space of a minus lambda I. Yeah? How do we do this? Remember, the null space is the set of all vectors such that a minus lambda I times x is equal to 0. Well, what's a minus lambda I? Remember, let me write it down again. A was equal to 3, 2, 3, 8. What's a minus 2 times the identity matrix? It's going to be 3 minus 2, which is 1, 2, 3, 8 minus 2, which is 6. Yeah, and I want to find the null space of this matrix, or basis for the null space, excuse me. How do we do it? Well, we take our matrix and we augment with zeros, of course. We perform a single row operation, subtract, take row 2 and subtract 3 row 1, 3 times row 1, and we get 1, 2, 0, 0, 0, 0. I have one free variable. Let's call it t. x1 is now negative 2 times t. So what's a basis for this eigenspace? A basis is negative 2, 1. Yeah, that's a basis for that eigenspace. What about if lambda is equal to 9? Pause the video, you can do this yourself. So if lambda is equal to 9, a minus lambda I becomes negative 6, 2, 3, negative 1. We want to augment with zeros and find all the vectors x and then pick out a basis, right? So performing some row reduction, we see that this is 3, negative 1, augment 0, 0, 0, 0. And we get our basis is what? Looks like it's going to be the set 1, 3. Yeah, that should work. What happens if you were to, I know what you're thinking, well, Dr. Benge, that doesn't make any sense, because if we let x2 be equal to t, then that means that x1 will have to be what? 1/3 times t, right? So you're saying, I know, boy gee howdy, wouldn't that mean that a basis is really 1/3 1? Isn't this a basis? And my answer is sure. Yeah, of course it's a basis. But remember, basis vectors are not unique. So this is totally a basis, and this is totally a basis. Why? Because if I scale this by a constant 3, it's still going to span this solution set. Yeah? Cool. All right. Question. If A is an n by n matrix, how many eigenvalues and eigenvectors does it have? Yeah? How many does it have? Well, let's do this by example. Let's let A be equal to 0, 1, 0, 0. Find the eigenvalues of this matrix. Yeah, pause the video, try it yourself. So we need to compute the determinant of A minus lambda I, right? So that's the determinant of the matrix negative lambda, 1, 0, negative lambda. Well, what's this determinant? It's just lambda squared, isn't it? And I set this equal to 0. The only solution is lambda equals 0. So in this matrix, remember the previous 2 by 2 matrix had 2 eigenvalues. This one has 1 eigenvalue. Yeah, exactly 1 eigenvalue. Well, what do we know about its eigenspace? So if I want to find a basis for, so lambda 0, I want to find a basis for the null space of A minus lambda I, right? Well, that's easy. I just want to take my original matrix, 0, 1, 0, 0, augment with zeros, and I'm done. Yeah? I immediately see that I have one free variable. What's my free variable here? It is x1, so x1 is free, and x2 has to be 0. So what's a basis for my eigenspace here? My basis is 1, 0. So in this example, I have only one eigenvalue, and I have only one eigenspace, and it's one-dimensional. I have only one eigenspace, and it's one-dimensional. Let's recall in our previous example. Here's our previous example. We had 2 eigenvalues and 2 different one-dimensional eigenspaces. That's interesting. What can we say in general? In general, the number of eigenvalues will be at most n, and the number of the number of eigenvalues is at most n, yeah, and the sum of the dimensions of the eigenspaces is also at most n. Yeah. Okay. Let's do an example. Show that if ax equals lambda x, yeah, where a is invertible and x is an eigenvector, of course, so it's not 0, yeah. Suppose we have an invertible matrix and x in this equation is an eigenvector. What can we say about the eigenvectors of A inverse? It turns out, show that x is an eigenvector for A inverse. If ax equals lambda x, where A is invertible and x is an eigenvector, show that x must be an eigenvector for A inverse. Yeah, pause the video, see if you can figure this out yourself. Well, we know that we're going to need to start with this equation, right? Let's multiply on the left by A inverse. And we know it exists because it's invertible. So A inverse times A is the identity. So on the left-hand side, we just get x equals lambda times A inverse x. What do we know now about lambda since A is invertible? Lambda cannot be 0. So we can divide both sides by lambda. So now we have the equation A inverse times x equals 1 over lambda times x. And we're done. So x has to be an eigenvector, and moreover, what have we found? We know that the corresponding eigenvalue must be 1 divided by lambda. And that's kind of nice. Yeah. Let's do another example. Show that if A is a triangular matrix, then the eigenvalues are just the entries on the diagonal. Yeah? If A is triangular, either upper triangular or lower triangular, it doesn't matter, show that the eigenvalues are the entries on the diagonal. Pause the video, give this a shot. Alright, so let's just see what A probably looks like, right? Let's suppose we're upper triangular in this case. And let's pick off the diagonal entries A11, A22, all the way down to ANN, with who cares up there and zeros below the diagonal. And what do we really want to compute? I want to compute the determinant of a minus lambda I, right? I want to compute the determinant of a minus lambda I and set that equal to 0. Well, what is a minus lambda I? A minus lambda I is going to be the matrix where star is unchanged, the zeros below the diagonal are unchanged, but the diagonals are now what? They're just going to be a11 minus lambda, right? a22 minus lambda, all the way down to ann minus lambda. And star is unchanged and 0 is unchanged. And how do we take the determinant of this upper triangular matrix? Remember, whenever we were talking about determinants, if you have a triangular matrix or a diagonal matrix, it's just the product of the diagonal entries, right? So this determinant now is equal to a11 minus lambda times a22 minus lambda. These are just the diagonal entries in this red matrix here, times all the way down to a sub nn minus lambda. And what are the roots? a11, a22, all the way over to ann. They're all eigenvalues. So whatever is on the diagonal here is going to be your collection of eigenvalues. And this is kind of cool because it gives some relationship between eigenvalues, and here we have the product of the eigenvalues, yeah, has some correspondence with the determinant here, yeah. And we get some general result that's similar to this example. Let's show that the determinant of a matrix A is just the product of its diagonals, or sorry, of its eigenvalues, yeah? We know that if we have a triangular matrix or a diagonal matrix, then the determinant is going to be, as we just showed, the product of the diagonal entries, and those diagonal entries are the eigenvalues. So we've shown this if we have a triangular matrix or a diagonal matrix. How do we show it in general? In general, we want to show that the determinant of a matrix is also equal to the product of its eigenvalues. So let's do this together since I don't think it's as obvious. Let's compute the determinant of A. Yeah? I know that the determinant of A, we've seen this before today, is equal to the determinant of A minus 0 lambda, right? We're going to use this as our inspiration. So let's first compute the determinant of A minus lambda I. Yeah? I know that this is a polynomial, a characteristic polynomial of degree n. Let's factor it. I know it's a polynomial. Let's factor it. And let's factor this as lambda 1 minus lambda times lambda 2 minus lambda times blah, blah, blah times lambda n minus lambda. So let's just factor the characteristic polynomial. And what do we know are the lambda 1, lambda 2, lambda n's? Those are the eigenvalues, right? Those are the roots of the characteristic polynomial. So if we set this equal to 0, we'll certainly get the eigenvalues. But I really just want the determinant of A. How can I extract the determinant of A from this guy? Just set lambda equal to 0. So if lambda is equal to 0, we get the determinant of A is equal to the determinant of A minus, mistake up here, I'm sorry about this, guys. It's A minus 0 times I. I'm so sorry. I apologize. So now we replace lambda with 0, but that's the same as replacing lambda with 0 in this factored expansion, isn't it? So I get lambda 1 minus 0 times lambda 2 minus 0 all the way down to lambda n minus 0, which is just the product of the eigenvalues. Sorry about my typo up there. And that's kind of interesting. All right, so let's do another example. Let A be a 3 by 3 matrix. We're bored with 2 by 2s now, so let's do a 3 by 3. 2, 0, negative 2, 1, 3, 2, 0, 0, 3. Try to find all of the eigenvalues and a basis for each eigenspace. Yeah. Pause the video. Try to do this yourself. You have all the tools that you need. So you're probably not surprised. We're going to start off with computing the determinant of a minus lambda I, which in this case is the determinant of the 3 by 3 matrix, our favorite, right? 2 minus lambda, 0, negative 2, 1, 3 minus lambda, 2, 0, 0, 3 minus lambda. Let's take the determinant. I'm going to expand what looks most helpful for me. I'm going to expand this along the, maybe the last row here. Yeah, let's expand along here. And I see 0, 0, that's nice. And I'll get plus 3 minus lambda times this, minus 0 times 1, which is 0. And this is super nice because it's already factored for us, isn't it? I see that we get 3 minus lambda squared times 2 minus lambda. And how do we find the eigenvalues now? We take our characteristic polynomial here, set it equal to 0, and let's solve for lambda. So we must have that our eigenvalues are lambda equals 3 and lambda equals 2. Easy peasy, right? So in this case, notice I have a 3 by 3 matrix, and indeed I have at most 3 eigenvalues. I have 2 eigenvalues, yeah? This one, my eigenvalue 3, is repeated. It's a repeated root, right? Later on, whenever we define this, we'll call that the algebraic multiplicity is 2, because it's a repeated root. And this guy has algebraic multiplicity 1 because there's only one root. Yeah? All right. So now let's begin our arduous task of finding a basis for each eigenspace. So suppose lambda is equal to 2. We really want to compute a basis for a minus 2 times the identity matrix, right? Well, I think that should be the matrix 0, 0, negative 2. 1, 1, 2, 0, 0, 1, augment 0, 0, 0. Yeah. Well, let's do some row reduction. I can immediately kill this negative 2, and I can kill this 2, so I can take this one, murder everything above it, and do some row operations. And I see that this should become something like 1, 1, 0, augment 0, 0, 0, 1, 0, 0, 0, 0, 0. And so I have one free variable, don't I? I know that x3 has to be 0. I know that x2 is a free variable. I know that x1 is going to be negative t. And so what's a basis for my eigenspace? And E sub 2 is going to be the eigenspace associated with lambda equals 2. And a basis here is going to be negative 1, 1, 0. Easy peasy, right? Let's do it again for lambda equals 3. Whenever we compute a minus 3I, we should get negative 1, 0, 2. 1, 0, or sorry, negative 2, sorry about that. 1, 0, 2, 0, 0, 0. And by adding these together, we see that we get 1, 0, 2, augment 0, 0, 0, 0, 0, 0, 0, 0, 0. How many free variables do we have in this system? I have two free variables, right? Let's let x2 equal to t. Let's let x3 equal to, I don't know, r. I don't care. What does x1 have to be now? x1 is negative 2 times r, isn't it? So what is an arbitrary matrix in our eigenspace? What does it look like? It looks like negative 2r, t, and an r. Remember, to find a basis here, we want to peel this apart in terms of r's and t's, and I see that I have negative 2, 0, 1 times r plus tiny vector 0, 1, 0 times t. Yeah? So what's a basis of this eigenspace? A basis of this eigenspace, and this will be E3, the eigenspace associated with lambda equals 3, is the vector negative 2, 0, 1, and the vector 0, 1, 0. Yeah? Hope you can see that over there. So what's the dimension of this eigenspace? The dimension of this eigenspace is 2. And the dimension of the eigenspace associated with lambda equals 3, or sorry, with lambda equals 2 is 1. Yeah? All right, so let's put this together now. Recall that our characteristic polynomial, char poly, because I'm lazy, yeah, the characteristic polynomial for this matrix was 3 minus lambda squared times 2 minus lambda. Yeah? And remember that the dimension of E sub 3 was 2, and the dimension of E sub 2 was 1. Well, that's kind of interesting. This gives us a definition. The algebraic multiplicity of an eigenvalue is its multiplicity as a root of the characteristic polynomial. And we say that, as another definition, the geometric multiplicity of an eigenvalue is the dimension of the corresponding eigenspace. Yeah? And in general, what can we say? The algebraic multiplicity is greater than or equal to the geometric multiplicity. Yeah? So the dimension of any eigenspace is going to be at most the multiplicity that you see as a root of the characteristic polynomial. And what's the highest that the algebraic multiplicity could be? What's the largest that the algebraic multiplicity could be? Well, it's the highest exponent that you could see in the characteristic polynomial, which is n, right? So this is always bounded above by the dimension of the matrix, by n. Yeah? Alright guys, so that's all that I have to say in this video. I apologize for it being a little bit longer than we're used to. I hope that everything makes sense. If not, just feel free to reach out via email, or I'm happy to set up a time to Zoom and we can talk about some fun mathematics. In the next video, we will talk about similarity transformations as well as diagonalization. So thanks so much for watching, guys, and I look forward to all of your questions, and I look forward to seeing you in the next video.